Okay, so this section's video is going to be a little bit short. We're just going to go over some of the basic information. I'm going to refer you to some examples, and then we will take a look at some of those examples in class and then have our work time as usual. So the last section from Chapter 7, something we won't be doing in AB, is talking about how integration is applied to science and statistics. So you can picture integrals so far have been useful where you're like finding area, but in general, remember it's the sigma is where it's morphed from. So an integral is used to sum up information. So anything that changes. Now, if values are constant, then usually these science and statistics problems can be solved by like simple multiplication, addition, algebra. But that's the point of calculus. It's all about momentary change and then finding about the rate of change or perhaps the total accumulated amount of change that may have occurred. So if a value is changing, we need to sum up the result at every moment or location, and this is accomplished by integrating. So that's what an integral will do. So when we're talking about science and statistics, with statistics we're going to look at the normal curve. And those of you who have had or have AP statistics, or just remember a little bit about it, the normal curve is like a bell-shaped curve. And there is actually a formula that will generate that graph. We're going to look at that in a little bit. For physics or science, there's some formulas that we'll use integration for. So work is equal to force times displacement. I'll use the D for displacement there, not distance, although often it's a positive distance we're looking at, or a positive displacement, which would be distance. Pressure would be equal to weight density times depth. So we use an H typically for the depth. So that would be, for example, if you fill up a bucket of water, there is more pressure at the bottom than the top, because at the bottom of that bucket you have the weight of the water exerting the downward force or pressure on top of what's at the bottom. Now for the last one there, force would also be equal to pressure times area. So these things all change excuse me, because perhaps when you're looking at work, you're applying an amount of force that varies as this displacement occurs. The example we'll look at in the book is you're like pulling up a leaky bucket, and as you're pulling that bucket up, water is leaking out of it, so there's less weight as you go, so there's a different amount of force necessary at each moment that you're pulling it up. Pressure and depth, of course, the depth hopefully is the obvious one there. At the top, at the surface, there's less pressure. Way down under, like say water, for example, you will feel more pressure being exerted. If you're swimming underwater, of course, that's why your ears, you'll feel some pressure when you're down at the bottom of a 10-foot pool. And then for force, looking at it and talking about pressure, a problem we'll look at there would be, let's say you have a tank of some fluid, and when there's pressure that's increased at the bottom, that is applying more force, more outward force on a tank, let's say, that's a cylindrical tank. And so there is more force being exerted on the tank at the bottom of it than the top because of that increased pressure. And so we'll look at a problem with that. So they're all about change. What we'll look at is, we're going to stick to keep it simple. We'll look at some of what I think are the key examples from the book. So we'll look at pulling up a leaky bucket. We will look at a conical tank of olive oil. Excuse me. We will look at a cylindrical tank of syrup. So apparently the authors were very hungry when they wrote this part of the text. And then we'll look at the normal curve, and how about this? Spinach. So it's all about food in this one, apparently. So what I would suggest or encourage is, with the guide, take a look at those problems in the text. Work on just kind of reading through whatever is maybe the most apparent or the easiest for you, however far you want to go. And what we'll do in class the next 2 days is we'll look at a little bit of each. We'll go over that formula for the normal curve, and we'll take a look at how integration applies.